So in section 6.3, we're going to revisit the concept of atomic mass, and we're going to contrast that with molar mass. So it's worth recalling that every atom in the periodic table has a characteristic mass, and this is the weighted average mass for that atom, and it's normally written below the element's symbol. So an entry in the periodic table might look like this. It has the symbol for the element. It has what we call the atomic number of the element, the number of protons that's in the nucleus, and then this one here, it's often called the atomic weight, and it has units of AMU, and that expresses the average mass of that particular atom in AMU. So for an individual atom that's like not, a mixture of isotopes, say something like a carbon-12 atom, those individual isotopes will have their own atomic mass, right? So this one here, sometimes they kind of distinguish that it's the weighted average by saying it's the atomic weight. But a carbon-12 atom, you'll probably remember, has a mass of exactly 12 AMU. A carbon-13 atom has a mass that's about 13 AMU. So it's important to realize that the atomic number is not related in any way to the atomic mass. Similarly, the mass number is only loosely weighted to the actual atomic mass. So one of the important qualities of the mole is that 1 mole of an atom weighs an equivalent number of grams as the mass of 1 atom in AMU. So that's, if we have an average carbon atom, right? An average carbon atom has a mass of 12.01 AMU. So then a mole of carbon atoms, we could say, has a mass of 12.01 grams for 1 mole. So 12.01 AMU for 1 atom, but 12.01 grams for 1 mole for an average carbon atom, right? Does it make sense? All right, for something like a carbon-12 atom that has a mass, an atomic mass of exactly 12 AMU for 1 atom, then a mole of those atoms would have a mass of exactly 12 grams. So the mass of 1 mole of a substance is referred to as its molar mass. And it doesn't matter whether it's carbon-12 atoms or donuts, the mass of 1 mole of a substance is called its molar mass, and it has units of grams per mole. So it's pretty simple. You can calculate this for an individual atom, you can calculate it for an average atom, you can calculate it for a molecule, okay? It doesn't really matter. You can calculate it for any object. So one carbon-12 atom has a mass of 12 AMU, a mole of carbon-12 atoms has a mass of 12 grams. 1 sodium atom, an average sodium atom, has a mass of 22.99 AMU. A mole of sodium atoms has a mass of 22.99 grams. A single chlorine atom this is an average chlorine atom, has a mass of 35.45 AMU. A mole of chlorine atoms has a mass of 35.45 grams. All of these things, we could say that this number here represents the molar mass, and we could say that a carbon-12 has a molar mass of 12 grams per mole. We could say that sodium has a molar mass of 22.99 grams per mole, or we could say that chlorine has a molar mass of 34.45 grams per mole. That would also be entirely valid. The same thing applies for molecular compounds or ionic compounds. 1 mole of a compound weighs an equivalent number of grams as its formula mass in AMU. So if I calculate the formula mass of water, I would take 2 times the mass of a hydrogen atom plus 1 times the mass of a oxygen atom, and that would tell me that one molecule of water weighs 18.016 AMU. Therefore, what I know is that a mole of water molecules is going to weigh 18.016 grams, or alternatively, I could say that the molar mass of water is 18.016 grams per mole, however I want to say it. They're all equivalent things. So the important thing to recognize about the molar mass is, just looking at the example for water here, I get 18.015 grams of water for every 1 mole of water. You see how I've got those 2 different units, top and bottom. So this guy can function as a conversion factor, and just like all conversion factors, it can be written either way up. But what this conversion factor converts between is moles and grams, right? Converts between moles and grams. So molar masses function as the conversion factor between the mass in grams of a substance and the number of moles of that substance. And calculating molar masses is a skill that you kind of get really adept at, but then you've also got to know how to use them, right? And you've got to decide what way up you're going to use the conversion factor. So this is a good example here of where we're going to go from grams into moles. So the question asks, how many moles are there in 2.54 grams of water? And it should really say how many moles of water, but it's not perfectly worded, this question here. So the first thing we're going to need to do is recognizing that we're converting between grams and moles, and that our key, our tool for doing this is the molar mass. So I'm going to go ahead and calculate the molar mass of water by adding together the mass of 2 hydrogen atoms and 1 oxygen atom. And now I'm just going to apply my conversion factor, right? So starting with grams, and I want to turn into moles. So I'm going to need the conversion factor that has grams on the bottom line, so it cancels out, and moles on the top line. So I'm going to need to use the inverse of the molar mass, aren't I, right? So that's what I've done there. So there's my number of moles. And it makes sense that it's less than 1 mole, because I know that a whole mole weighs about 18 grams, and I've got less than 18 grams here. So therefore I should have less than 1 mole. So we've seen 2 conversion factors so far. We've seen Avogadros number, and that functions as the conversion factor between the number of moles of a substance and the number of objects. And what we want to remember is that when I'm going towards moles, I multiply by 1 on Avogadros number, and when I'm going away from moles towards the number of objects, I multiply by Avogadros number. And so now we've just introduced this second conversion factor, the molar mass, and that allows you to convert between the mass in grams and moles. And again, when I'm going away from moles, when I'm going from moles to mass, I'm going to multiply by 1 on the molar mass. And when I'm going from mass to moles, I'm going to multiply by the molar mass itself. So keep in mind that when I'm heading towards moles, oh, hang on, sorry, wrong way around here, my error. When I'm going from mass to moles, I multiply by 1 on the molar mass, and when I'm going from moles to mass, I multiply by the molar mass. So what you want to keep in mind is whenever I'm heading towards moles, I always have a 1 on the top line of my conversion factor. Okay, so this is just kind of like some little detail here, right, about these things. So Avogadro's number is a measured number. It's the number of carbon-12 atoms measured to be in 12 grams exactly, right? Or as near as possible to exactly 12 grams. And the most up-to-date value that we have for it at the moment goes out to about 7 decimal places. Okay, so here it is here. And, they might have added a couple more in the last year or so. Typically, chemists will use Avogadros number rounded off to 4 significant figures, but they will treat it as though it's an exact number. That is, they'll treat it as though it has infinity significant figures. That being said, while this is the most common value that you see people using, like, every day, the important thing for you is not to fret about memorizing this all the way out there to 8 significant figures, but rather just to make sure that you always use the value given in the data sheet that you've got. So that might be the data sheet that comes with an exam, or it could be the data sheet that comes with Alex or something like that. All right. Key thing with all of these values is just use the one that's given to you in those circumstances. And then you won't have any issues. Okay, AMU and grams are related to one another, and it's a pretty simple relationship to remember. If you remember that in a Avogadros number of carbon atoms, we have 1 mole, and that will weigh 12 grams, you can get the relationship between AMU and grams. So in an Avogadros number of carbon atoms, we have 1 mole of carbon atoms. We also know that there are 12 AMU for every 1 atom of carbon-12. So atoms of carbon-12 will cancel out like so. We also know that in 1 mole of carbon-12 atoms, there is exactly 12 grams. And using this factor, we can get the relationship between AMU and grams, because you can see here that also the 12 will cancel out. So what we know is that there are 6.022 by 10 to the 23 AMUs in 1 gram, i.e. there is 1 mole of AMU in 1 gram. All right, that's it. So either way, however you spin this conversion factor, kind of means the same thing, doesn't it? All right, okay. So these are all equivalent statements here. So that's the general deal there. There are a mole of AMUs in 1 gram. Alternatively, there are 6.022 by 10 to the 23 AMUs in 1 gram. Okay. So sometimes you will get a question where you have to take AMU and turn it into grams. So this one says, how many grams does a molecule with a mass of 105.42 AMU weigh? And obviously the answer is not many, because 1 molecule doesn't have, doesn't weigh a large number of grams. But let's do the conversion. We've got 105.42 AMU, and we know that in 1 gram there are 6.022 by 10 to the 23 AMU. So AMU would cancel, leaving me with grams, and there's my answer. You see it's a very small number. Okay, when you put this into your calculator, this is important how you enter it. You're going to do 105.42 times 1 divided by, and where this is where it gets important, you need to use the scientific notation feature on your calculator, or you will get the wrong answer. So when you put this into your calculator, make sure you use that scientific notation feature. You don't want to be putting it in like that, because that will lead to the wrong order of operations. Plus it's a whole bunch more characters to press, which just kind of lends itself to making more errors. Okay, so that concludes this short video on atomic masses and molar masses and explaining how they are related.